See your screen now.
Awesome. Thank you very much. And thank you for the introduction. I'm going to be talking about phylogenetic diversity index and phylogenetic diversity statistics. And I'm going to define it in a minute what it means. And sorry I couldn't be there in person. And it's a horrible 3 a.m. here, but I'll do my best. So let's first talk about why do we care about measuring diversity of organisms. And the first thing that probably comes to most of people's minds when you think about diversity is conservation biology, because with all the worrying things that are happening today in this world, we want to be able to preserve as much diversity as possible. And to do that, we need to be able to objectively quantify diversity. And on the other end of this, pathogens, they will probably want to limit diversity as much as possible, because with low diversity, it's easier to control pathogens. And in general, diversity is one of the core concepts in the ecological theory. And so to be able to test hypotheses in ecology, you often need to be able to objectively measure diversity. So let's now talk about how to do that. And there are probably two main schools of thinking. One is functional diversity, or more broadly phenotypic diversity. There you define some traits, some observable traits, and you measure them, and you kind of end up with a multidimensional trait space like shown here. And then you try to define an objective index on that multidimensional trait space. This is a very powerful approach. The difficulty there is that it's often hard to know which traits to include in the analysis, and also generally it's often tricky to be able to objectively quantify traits, and often traits are not independent. And so this is one school of thinking, and another, perhaps a little bit more straightforward, although there are its own caveats there, is measuring the genetic diversity directly. And so there, the most popular index is Phylogenetic Diversity Index, introduced by Faith in 1992, and this is what I'm going to focus on today. Many of you are probably familiar with the index, but I'm going to define it real quick. So phylogenetic diversity, or PD for short. So just imagine that this is a tree that we're given, and we're interested in a subset of taxa shown here as A, B, and C. And then PD, you look at the smallest subtree that connects A, B, and C. And also in our case, we connect it to the root. And so then the PD index is the total length of the branches in this subtree. So basically the total length of all the orange branches here. And so the really good thing about PD is that it gives us a very simple but objective way to compare different sets of taxa. So if we have a set ABC and another set DCE, then we can compare their diversity using PD. And so I've added branch lengths here, and so you can verify that for ABC, the PD comes up to 20, and for DCE, it's a little bit higher, it comes up to 27. And you can just also visually observe that DCE, the set DCE does seem to cover a little bit more ground on this tree than ABC. So more generally, you don't want to just compare two sets of taxa, but you probably want to compare your set of taxa to everything else. And so what we would ideally have is a distribution like this, where you have different PD values and how frequently they appear on the tree. And then if you have that, for example, in our case, for all three taxon subsets, then when you're looking at the set of interest like DCE here, you can see where it is in the distribution, and you can see how does it compare to everything else. And then with that, you can do hypothesis testing and other things. So this is what we would ideally have. But the difficulty here is that to compute this distribution, at least naively, you can imagine that we have to go through all n choose k subsets of taxa on our tree, And for larger k, this quickly becomes infeasible because n choose k can be a very, very large number. And so, but it turns out what we can do is compute kind of a feel of a distribution of phylogenetic diversity. So what I mean by this, we can compute the range, the mean and the max values of the distribution, and also two moments. We can compute the expectation, so the average, and the variance. And then so using this for statistics, we can already do hypothesis testing, and we can get an idea of how the distribution looks like. And so I'm going to refer to this for statistics as PD statistics for short. And so this is what we focused in our work, but we were not the first ones who came up with this idea. And so there's quite a lot of prior work on computing PD statistics. And most of prior work was focused on computing the maximum because it was proposed to be used for conservation. And there is a linear time algorithm by Spillner et al. For any k, it can compute the maximum PD in linear time. And then for the minimum, there's also some very recent work by Manson et al. They proposed an order of k cube n algorithm for computing the minimum for a given k. And this is nice work, but for larger k, this can be quite prohibitive. So we wanted to do there something a little bit more, a little bit better. And then for average and variance, there's also prior work by Tsirgianis et al. And this is really nice work and really nice algorithms. The only problem there is that they compute those statistics inexactly. So they give an approximation, but they don't really give you an approximation guarantee. So for larger trees, again, this can be problematic because you're not sure how close those estimates are to the truth. And then so our contributions were that we compute the minimum in order of kn. So that's a nice improvement compared to the Manson et al. Algorithm. And then we compute the average and variance exactly using this runtime. And this runtime is a little bit more costly than the minimum, but you'll see that we can still process trees with tens of thousands of taxon. So another important contribution of our work is that we don't just give you 4 numbers, so we don't just compute those statistics for the entire tree, but we can compute it on each individual clade level. And we also compute it for different values of k. So what I mean by this is, imagine we have a tree like this, and we're interested in a subset of taxa A, B, C, D. And then perhaps, and this is just a hypothetical distribution, not real numbers, perhaps in the overall 4 taxon distribution, this ABCD subset is somewhere here. But when we zoom in on a smaller clade, for example, this clade where we have A, B, and C, then perhaps in this 3 taxon world, ABC is somewhere here in the distribution within that clade. So by providing those statistics for all clades, we can see how the diversity of your subset is, how is it evolving and how it is distributed across the tree. And I'll show an example in a bit of how it can be useful. So let me run you quickly through one of those algorithms for computing the minimum. So we use dynamic programming there, and this is just a simple example to run you through it. So the internal nodes on this tree are labeled 1, 2, 3, and this is what are the rows of this dynamic programming table. And then as columns, we have different values of k from 1 to 4. And so we go one by one in this table through rows, and we start with node 1 and k equals to 1. And so in that subtree, we have 2 options for we computing the minimum PD. So for k equals 1, we need to select either A or B. And since we're doing minimum PD, we want the one with the shorter branch. And so in this case, this is A, and this is what we put in this dynamic programming table. And then for k equals 2, we have only 2 taxa here, and so we only can select A and B. And for k equals 3 and 4, we cannot do anything because we have only 2 taxa here. Then when we move on to node 2, and it's a similar story here between Between C and D, we choose D because that's a shorter branch, and then CD for K equals 2. Then it becomes a little bit more interesting when we move higher, when we go to the root of the tree. For K equals 1, we have two options. We can select that one taxon from the left. In this case, we know that from previous computations, we know that we select in A, and we just need to add the length of this branch here. And then if we go to the right, and we know that we select in D, and we need to add this the length of this branch. And comparing those two options, A is the better option because it's shorter. And then we'll move on to K equals 2. For K equals 2, there are even more options. So those two taxa, both of them may come from the left. In this case, we're selecting both A and B. Or both of them might be coming from the right. Then we're selecting C and D, as shown here. Or we can choose one from the left and one from the right. And we know that from the left we choose an A, and from the right we choose an D. And so comparing these three options now, this one turns out to be the better one, and we put this here. And then when we move on to K equals 3, there are again several options we can select out of those three taxa. One comes from the left, two from the right, or two from the left and one from the right. And comparing those two options, it turns out that the latter is better, and this is what we go with. And for K equals 4, we have to select everything. So hopefully I gave you an idea of how this works. It's pretty straightforward. And kind of on a more abstract way, on a more general way, if we're looking at a larger tree, and we're looking at a fixed node in the tree and a fixed value of K, then we have to go through different options of how we distribute that K between left and right. So nothing from the left, and then all K have to come from the right. Or we can select one taxon from the left, and then K minus 1 from the one from the left and K minus 1 from the right, and so on. So when we're doing computations for one cell of this dynamic programming table, in the worst case, we have to go through an order of K different options of how we distribute that value between left and right. And then the size of this dynamic programming table is n by K, so the overall number of operations that we do is nk squared. But it turns out that if you do the counting of your operations a little bit more carefully, then and it was shown in 1990s in two independent works by Tamir and Hallerson et al. That when you do this counting a little bit more carefully, your actual runtime is only an order of nk, instead of, so you basically saving a factor of k here. That result in the one lemma, because the results there were kind of specific to the algorithms, but on more broadly, when you have a dynamic programming of this sort where you distribute in between left and right, you can show that you can save a factor of k there. So if you run into that, I'd be happy if you use this lemma. So this was the minimum algorithm, and we're computing it the minimum for all clades in order of kn. And then for the maximum, you can do the same thing for all individual clades altogether in this runtime. And for the average PD and variance PD, it's kind of similar to the dynamic programming approach, just a little bit more complex because you have to deal with binomial coefficients there, because we're computing those statistics exactly. And because of those binomial coefficients that can be very, very large, there's a bit of a runtime overhead here. But so we're computing this post statistics for all clades, and as you saw in this dynamic programming table, we computed for different values of k. And so this is how it looks in practice. This is a experimental runtime of those algorithms, and what I want you to take away from this graph is that we ran this up to 10,000 taxa. So, and for a tree with 10,000 taxa, we compute all 4 statistics for all clades and all possible values of k in under 1 hour. And if you're not interested in all possible values of k, but let's say you're interested in k up to 100, then we can run it for trees with hundreds of thousands of taxa in just a few minutes. So let me now give you an example of an application of this computation. So in our lab, we're interested in influenza A viruses and interface between pigs and humans in terms of influenza A viruses. And many of you might be familiar that influenza A viruses occasionally jump from pigs to humans, and also they very often jump from humans to pigs. And so the most famous example of a swine to human transmission was the 2009 pandemic that probably all of you remember. But then it also happens on a much smaller scale, just kind of one-off infections. And there are, after 2010, there were documented around 500 cases of swine to human transmission events. So this is kind of one-off infections with swine influenza. And so swine influenza is very diverse. And so our hypothesis there was so we have this large number of cases of swine to human transmission. So we can leverage that, and we can look at the diversity of those cases as compared to the within clade diversity of swine influenza. And then perhaps more diverse, if the spillovers are more diverse, then our hypothesis there was that there's a higher probability that this clade that we're looking at is better adapted to be able to transmit from pigs to humans, and potentially eventually can cause a larger outbreak. And so this is how it looks. This is one of the lineages of swine influenza. This is a massively subsampled tree, but what you can see in here, hopefully you can see in here, in red are shown those swine influenza cases that were isolated from that were collected from people. And so you can see that they're kind of all over the place here. So there's actually overall there's a high diversity of those cases. But now with using PD stats, we can zoom in on clade level and see how those red cases compare to the within clade diversity. And this is what we try to do here in this graph. And basically the larger the node is and the redder it is, basically it's saying that the diversity within clade diversity of those spillover cases compares favorably to the average within clade diversity.
Alexey, you have 2 minutes.
Oh, thank you. I'll try to wrap up quickly. And so with that, we can see that, for example, this clade seems to have a high diversity, and we do know using animal models that this clade actually does represent higher zoonotic risk. But this is just to show you that if you have your own data set and you're interested in a subset of taxa, for example, displaying a certain morphological trait, then you can do this type of analysis and see how PD compares to the within clade diversity. So just to summarize, we developed efficient algorithms for computing PD statistics on phylogeny, and we can process trees with tens of thousands of taxa. And so we're computing those, as I've just shown, we're computing those statistics for all clades and different values of K. And you can use this code, and it's available on GitHub. And there's also the QR code here that leads to the same link. And you can use this to test diversity-related hypotheses on your data. And just to wrap up, quickly want to thank everyone who contributed to this work. Sid Grover, who led the work, and Oliver Wallenstein at Iowa State University, and then Tavis Anderson and Amy Baker at the National Animal Disease Center. And also want to thank our funders, and thank you for listening. And if there is some time, I'd be happy to answer any questions.
Thank you. So any questions from audience? Okay, thanks.
So I'm curious about the flu phylogeny, because if I remember correctly, flu has something like 7 genomic segments. So it would strike me that what you would want is the trees for each segment. Am I thinking about this wrong, or, basically?
No, you definitely are not. Yeah. There are in influenza A there are eight genomic segments, and this is just one of them. This is a hemagglutinin. Most of influenza work is done on the hemagglutinin because it's a major surface protein that is targeted by antibodies, and so most of evolution is happening in the at least related to kind of antigenic evolution is happening in the hemagglutinin, and so most of people look at that. But ideally, you're right, and we would look at all segments altogether, and perhaps we would do the averaging across different segments, and we would somehow do the comparison across different segments. It's just would become a little bit more tricky, but that would be an ideal way to go.
Okay.